Hi everyone. My name is Amanda Cook. I'm in the last couple of weeks of my PhD at the University of Toronto, and I'm going to talk about what CHIME FRB can tell us about the Milky Way's halo. Forward. Okay. So I'll try not to repeat Liam too much. The question is, what are fast radio bursts? And the answer is, I don't care, or it doesn't matter. They have some observational properties that are nice. And so these properties are that they're ridiculously bright. They're impulsive, millisecond duration, and they're polarized, and they're radio. They come from galaxies other than our own, and they're perfect point sources. What this means is as they travel towards us, the density, distribution, and magnetization of any intervening media is encoded into them. This is through dispersive delay and scattering, Faraday rotation measure, and potentially lensing. So every FRB we detect is a cosmic Pierce point of any ionized plasma, no matter how dense, essentially. Wouldn't it be nice if we had them all over the sky? In comes CHIME FRB. So CHIME is the Canadian Hydrogen Intensity Mapping Experiment. It's located in British Columbia, Canada. It's a radio telescope operating between 400 and 800 megahertz, and it surveys the entire northern sky every day. I did say northern, which means unfortunately not LMC and SMC, but we do get Andromeda and its extended halo, which is pretty cool. It has a data rate of a terabyte per second raw, which I've been told is equivalent to all of North America's telecommunications, kind of crazy. And it produced just that, FRBs all over the sky. So this is what the sky map of FRBs look like from CHIME FRB from our first year of operations in our first catalog. And this is what that first year of operation looks like compared to all the other FRB detectors in the world. You can see where we turned on and where our first catalog cutoff was. Definitely made a substantial impact, but that is not to brag. There are definitely problems with CHIME FRB, and one of them is that we don't have fantastic localizations. Our localizations span, at best, a couple arc minutes, and at worst, a full degree. I'm going to talk about the dispersion measure of fast radio bursts today. So dispersion measure is an integrated column density of mostly free electrons along the line of sight, only free electrons to about 1 in 1,000, pretty good. The nice thing about an integrated column density is that it's additive. So we often decompose the measured DM into 4 contributions, starting with the host of the fast radio burst, its DM contribution. And then you have the intergalactic medium and any intervening halos, followed by our galactic contribution, which I've split up here into the disk and the halo contribution. I don't need to motivate to this crowd why we're excited about measuring the halo contribution and learning about the density of the halo, but I will say that it is additionally interesting for FRB scientists because it's often considered just a foreground we need to subtract in order to get at this IGM contribution, which is very exciting, or to infer the distances of FRBs from their DMs. Also, if you just take different observables, models for the Milky Way halo, cosmological simulations, and you use them to estimate the DM halo contribution that you would see for each line of sight. Currently, our estimates span like an order of magnitude, so it's not constrained well enough to use them just from models. So the idea of this project is very simple. If every FRB is from an extragalactic source, in order to come to us, it has to pass through the entire Milky Way. And so every DM that you measure from an FRB is an upper limit on the entire galactic contribution. We have a lower limit on the disk contribution from radio pulsars, which we have tons of in the disk. So if you subtract the upper limits from FRBs and the lower limits from pulsars, you get upper limits on just DM halo. So now we take this picture and we turn it on its side. The idea is as you detect more and more FRBs, you'll get these FRBs that have dispersion measures that are dispersion measures from their host that are like statistically small and are very nearby, so better and better estimates of just the halo contribution. This plot is dispersion measure versus galactic latitude, where I've cut off galactic latitude at a sign B of 0.5, or about 30 degrees, just to avoid low latitude structure. On the top in the triangles are FRBs. They're coded by how many times we've seen a particular source, and then on the bottom are pulsars, which are colored by if we detected them or not. So let's describe the lower limits due to pulsars first. There are fantastic models for this. I'm using popular galactic free electron models, NE2001 and YMW16. Also this newer model by Stella Ocker, where she just assumes that the disk has a slab geometry and estimates the scale height. So for the yellow, that means that's just the errors on this slab geometry disk, but the other two, the span shows how much it changes as a function of galactic longitude, so how much it varies. Okay, and then on to trying to estimate the boundary of the halo. So it's not like immediately obvious how you fit a boundary to a set of data points. We did this in a couple ways, essentially just allowing for more or less structure as a function of galactic latitude. The first one, it just assumes a polynomial form and maximizes the area from the dm equals 0 line to the boundary. We also did one that allows for a little more structure, where it's just a low S fit, which if you don't know about low S, it essentially just penalizes for outliers. This is assuming that the dm halo contribution is constant. So if you just plot it on top of this Stella-Ocker model for a slab geometry of the disk and assume that there's only one value for the Milky Way halo, that's kind of the tightest constraint you can get. And then this is not a physical model, but just to guide the eye on how close these are to our best line of sight, a constant model. So depending on which line of sight you're looking at and how much structure you want to allow in your model, our upper limits on the total galactic contribution span from 88 to 141 of these horrible DM units, or just for the halo span between 52 and 111. You can compare these to what was predicted from the models that I was talking about that span an order of magnitude. So the colors here, basically if you see something in red, it's disfavored for all of our sight lines and models. Yellow is good for some and bad for other sight lines and models, and green is supported by all of our sight lines. The first plot there shows the Yamasaki and Tatani model, which is the only one of these suite of models that makes galactic latitude, a model estimates as a function of galactic latitude. The other ones, this span just shows either different masses you assume for the Milky Way, different feedback implementations, or the span over latitude and longitude. Kind of summary is the NFW profile, where you assume that the baryons follow the dark matter is inconsistent, and that's not new. We knew this. If you modify it to allow for baryonic feedback, which was done by Matthews and Prochaska in 2017 in that modified MNFW profile, it becomes consistent. Similarly, in the PEN 99 model, the model is more consistent when the effective baryonic feedback is maximized. Most of the higher mass scenarios of the models were ruled out. There's this Dillig et al. 2015 cosmological simulation that predicts DM halo values explicitly that remains super relevant. There's also one line of sight which can kind of tell us a lower limit on how much we expect from the DM, which is from the repeater in the M81 system. And it seems like this Miller and Bregman model is a little bit too low in that case, unless you assume that the Milky Way halo is very clumpy, or assume that the contribution from M81's halo is much larger than our own halo, which would kind of make sense given it's a much more complicated system, but it still seems a bit small. So these are the first latitude-dependent constraints from FRBs on the Milky Way halo. I've kind of listed these numbers again, but this is now becoming a slightly old sample, so I just kind of want to talk about what's next. You can also scan the QR code. It's Cook et al. 2024, but that's a really common last name. So good luck. So as Liam was talking about, there's a new era coming in FRB science, which is enabled by tons and tons of precisely localized FRBs. You can talk to Adam Landman, who's sitting in the second to last row over here, if you want to learn about how CHIME is going to do lots of these precise localizations. But these precise localizations will allow us to infer the remaining DM components and then map baryons throughout the universe, as Liam was talking about. But also for CHIME FRB, we've only released our first catalog, which is from our first year of operations. We are going to release a 10 times bigger catalog in months' time, like early next year. So I'm hoping this will allow us to map out the Milky Way halo DM contribution, both in latitude and longitude, so another dimension, as well as test for anisotropies towards M31, so due to the local group contribution, as well as above and below the plane. So yeah, happy to take questions.
Okay, thanks for the group talk. Is there evidence for larger DM in the direction where we know there's the Fermi bubble?
So, that's a good question. I didn't test for it explicitly. What direction is the Fermi bubble?
Somewhere above the galactic center.
Okay. So I have tested just above and below the plane. The problem is we have way more exposure above the plane than below the plane just because of where CHIME FRB is in the sky. So I'm hoping with this updated sample we'll be able to meaningfully do these anisotropy tests. But right now if you do it, it's hugely dominated by just having like 10 FRBs versus 80 FRBs in wonder.
No, but this would be in longitude, not latitude.
Oh, I've also only just tested inner and outer galaxy, which should be very obvious because you also have to go through way more disk, and I can't see that statistically either between the two samples.
Okay, well, nice talk. So I guess if I was just like a simple question of just trying to get more into this world, like if I was trying to do measuring dispersion measure towards some external source, like of the IGM or some external galaxy's CGM, then I guess that would be that measurement would highly depend on what I assume for the Milky Way CGM dispersion measure contribution.
Yeah.
And as you show, there seem a variety of different predictions of what that should be. So is it like a standard model that people in the field usually assume, or is it just everyone's using their own model?
I don't think we have a great prior on that, basically, is what I would say. I think that it's what we need to do next and like use populations of FRB to make some statistical argument about what the DM contribution is. You also have the exact same problem if you're trying to infer something about the IGM from you've given the host DM contribution. So there's a lot of like degeneracies in that we don't know these exact contributions. In terms of just what people have been using, I see a log model applied to the Milky Way a lot. A lot of people will just take these limits I said and then use anything uniform under them and use some kind of MCMC. But I think we have to tighten these up in order to make meaningful conclusions.
Yeah, very nice talk. I had a question about using the pulsars to get the foreground dispersion measures. Have you looked at the Magellanic Clouds? I believe there are some pulsars in the clouds that would give you a fuller path to check the dispersion measure. Is that something you've been able to look at? Yeah, so we can't compare it directly because we don't have them in our in our field of view. That said, so the small and large Magellanic Clouds have DMs. There's pulsars in there that have DMs of 50, 60. So it's actually like, because that's a little bit into the halo, it's much larger than what you would see, I think, in that direction just from the disk alone. But it's still a very insignificant fraction of the total halo, yes. Okay, I mean 50 or 60 is similar to the number you had there, so that...
right, so that would be above the, it would be 50 or 60 on this plot, so it's actually quite a bit below, you know what I'm saying? The 50 I was saying is between the galaxy and ours.
Okay.
They would fit in that nice gap.
Thank you.
So that was great. When you analyze the sample of 5,000, how well do you think you understand the sort of DM selection function, which can prevent you from finding extragalactic low DM bursts because they masquerade as galactic pulsars? That's
a really good question, and I think, so when we did it here, we just didn't worry about it because this gap is so big. Like, it seems like when we did it here, it was enough, even if there was absolutely no halo contribution, you wouldn't expect to detect any FRBs closer just as a simple, we don't have enough volume between where we're starting to detect these FRBs. And I think, I haven't done the test yet for 5,000 FRBs, but we'll do a similar test where, we can see like if we would actually be expecting to detect things so close to us, and if it will matter that we do have a selection effect where we select preferably only DMs above these galactic models, which right now it wouldn't, but if we had much better constraints, it would matter.
Time for two others with that person.
So I have a silly question. So for all these FRBs images, we're 100% sure they're outside the so they are actually setting up they do not reside in the
Okay, you could make an argument, right? So for every FRB that we've localized so far, it has been had a very large external excess dispersion measure, and it's been localized to a galaxy other than our own. That being said, I couldn't prove that to you for every single FRB in this sample, but we've yet to be wrong about the excess DM meaning an extragalactic source.
So just to have a sense, like among all of these triangles, how many, like what percentage of this has like localized sources that we know?
For these particular triangles, if they are not red, they're not localized, basically. Because we would allow, for the red ones, we detect it more than once, which means other teams can go ahead and pinpoint it for us. we basically can't do the localization to a single galaxy ourselves unless we make some probabilistic argument.
Just one more question. No.
So this may be a bit of a tiny question, but for the repeating sources, is there, in my mind, more data is good, right? Is there any way that like those repeated sources will constrain the dispersion and like try to piece apart what it is that is, you know, in that kind of smashed together signal, or is that not really how this works?
You could definitely get a better estimate of the dispersion measure, a better estimate of the scattering, the RM, from having more bursts, especially with higher signal to noise. I would say, just as far as baryon science goes, the uncertainties due to the degeneracies in the 4 components are much larger than the uncertainties due to just poor DM measurements. You can't see any of the errors on, like the errors are all smaller, on the DM are all smaller than the points on the graph in these plots. So yes, more data is better, and sometimes it even changes a little bit. But no, it won't improve the baryonic science we can do yet.
So I think let's thank Yolanda and the rest of the